Wow, this has been a long series of lectures for me to teach, for you to watch and listen. And yes, this is the final lecture of week 4 of the class Neuronal Dynamics. I will use this final lecture to make a transition from the two-dimensional neuron models to the nonlinear integrating fire type models that we have seen in week 1. And this is important because it's with these reduced models that we will work for the following 2 or 3 weeks. In order to make this transition, I will do yet another separation of timescales. I will assume that the auxiliary variable w is slow, and that means that most of the time w is indeed constant, and we can exploit that. Now, before I go into the mathematical details, let me remind you of the motivation. Why do we do all this? Well, cortical neurons spontaneously emit spikes. And you see here, in the total period of 5 seconds, there are only 2 spikes. That means spikes are sparse. They are rare events. Most of the time, the membrane potential is fluctuating in some regime subthreshold. It's fluctuating around some reference potential, or maybe we could say around the resting potential. And then the aim of modeling is to say, when is the moment, when is one of these rare moments that the neuron is going to emit a spike? Moreover, why do we see these fluctuations? Why do we see this up and down? Can we predict the subthreshold voltage with a neuron model? So, we have seen a class of two-dimensional neuron models, and these neuron models can be analyzed in the phase plane. This is the first variable, the voltage variable, horizontal axis, second variable, auxiliary variable w, vertical axis. And now separation of timescale means that the time constant for the second variable is much slower than that of the voltage. So this is our slow variable. That means w only changes a little bit. If you look at the derivative dw dt, then this is g over tau, but tau is big, so the change in a small time step of w is small. And this means that the flow errors are nearly horizontal all the time. So if this is a stable fixed point, then in the presence of some time-dependent stimulating current, the membrane potential would fluctuate up and down, while the w variable hardly changes. If we have a big input, then the voltage variable might be kicked up here, from which it goes very rapidly upwards. Then it turns around, it follows the U-node line, and then there's a rapid jump down before it goes back, and then it will again stay a long time close to this resting state. So the flux most of the time is nearly horizontal, except in the neighborhood of the null line. As we have seen, if we reduce the Hodgkin-Huxley model to 2 dimensions, then we have exactly this kind of diagram with the U-node line and the W node line, and these node lines will have several fixed points, and this is the stable fixed point. Now suppose I give a strong stimulus. If there's a separation of timescales, if W is slow, that means all the arrows are nearly horizontal, so there's a rapid rise towards a high voltage, high positive voltage. And this is the peak of the action potential. Then it stays a little bit up here. And it's at this moment that W starts to change. W starts to increase. And then we have a rapid downward movement. And then this is vertical here. And then W decreases again. So you see the total range of W in this scale is about 0.5. during a spike. But if the neuron is not spiking, if it's just receiving weak time-dependent input, then it's basically sitting here, and W is always equal to its resting value. So we can exploit this. W is always close to its resting value. That means in the first equation, where I have the voltage equation, where I have a dependence on the voltage NW, I don't really need this second variable. I can replace this by its constant value. And this replacement should be true in the neighborhood of this resting state here. It's not true up here during a spike, but down here, where the neuron spends most of its time, down here it's true. W is always very close to W rest. Now, we can plot this function now. I evaluate for fixed W rest. I evaluate the function f of u. And now this is now a function of a single variable. It's a function just of the voltage. That's a fixed parameter. That means I can rewrite this as a one-dimensional differential equation with some nonlinear function f of u. And this is how this function looks like. Now if we zoom in just into this region here, then what we find is that this function f of u has a linear part, and then it bends over quite rapidly. And in fact, this rapid increase can be described as an exponential part. Now this is in fact a nonlinear integrated fire model. And the specific nonlinear integrated fire model would be one which is a combination of this linear part plus an exponential part. In other words, an exponential integrated fire model. Now we can interpret this vertical axis, which is f of u plus r times I, for the moment set I equals 0, then this vertical axis is the derivative of the voltage. And then I can use the arguments of week 1 and say, well, if the present voltage is here, then the change is positive and if a flow towards the resting potential. If the voltage is here, the change is negative, we are below 0, ddtu is negative, flow in this direction. If we are here, it will increase further. Now let's now jump back to this model here. It will increase further. Now in this reduced one-dimensional model, it would in fact flow up to this additional fixed point up here. That's in fact the moment when the action potential reaches its maximum. And at this point we should go back to the two-dimensional neuron model and say now it does the flow in the two-dimensional phase plane, W increases, we have the downswing and so forth. And all this change of W, all this downswing is replaced by a threshold process. If this variable hits the threshold theta reset, then the voltage is reset to some new value UR, which might be below the resting potential or above the resting potential, depending on the type of neuron we are describing. Thus, during spike initiation, the two-dimensional neuron model can be replaced by just a single one-dimensional nonlinear integrated fire model. And the specific integrated fire model that results from this kind of analysis is the exponential integrated fire model, which has a linear part and an exponential part. Now, interestingly, if you do this analysis, the exponential part is rather sharp. We have changed here this parameter delta. If delta is a big number, say 10 millivolt, then we get a slow increase. If delta is a small number, like 2 millivolt, then we get a very rapid increase here. And this is the zoom into this kind of picture. That means as soon as the voltage is above this turning point, the change ddtu is very, very rapid. It's like a very rapid upswing of the action potential, and it doesn't really matter where we stop it. Now, in the limit, the delta becomes smaller and smaller. It becomes really a sharp threshold-like transition, and we are back to the leaky integrating fire model. The standard linear integrating fire model with a decay term. Now let's come back to our spontaneous activity picture of the awake mouse in vivo. The aim is to predict the spike initiation points. Now the spike initiation points are well predicted by this model. That's what I would expect, because during all this time here, in this subthreshold regime, W stays very close to the resting value, and it's only during the downswing of the spike and during the phase afterwards, after a spike, the W is not equal to W rest. Now, if our aim is just to predict the spike initiation point, and maybe also to predict the subthreshold fluctuations, then we don't need the W variable. We can replace the W variable by a reset. And this is essentially why such an exponential integrating fire model works so well to predict spike times. The same current is injected into a real neuron and an exponential integrating fire model. The real neuron emits a spike here, and so does the exponential integrating fire model. Spike initiation is perfectly well predicted. Here again, spike initiation is well predicted. The subthreshold membrane potential is well predicted by the model. It's only during the phase after the spike, where we expect that additional processes come into play, that the exponential integrating fire model is not as good. But if we add adaptation and refractoriness, as we will do in week 7, then this part can be covered as well. So we have reduced the two-dimensional model to arrive at the exponential integrating fire model. However, we could have done this in a single step coming from the Hodgkin and Huxley model. Let's replace the M variable, the fast gating variable, by its instantaneous value. H and N are slow. Let's replace H by its reference value at rest and N by its reference value at rest. Then we have just a function which depends on the membrane potential, and these are parameters. For fixed parameters, I just have a function f of u, and this function is the exponential integrating fire type model. It has a linear term and an exponential term. Now this nonlinear integrating fire model needs to be complemented by a threshold and reset mechanism, and then we are done. So let me summarize what I said. If we have this separation of time constants so that W is the slow variable, then the neuron that stays most of the time close to its resting state can be treated by a model where W is treated as a constant. W comes into play mainly during the downswing of the action potential, not during the initiation of the action potential. This kind of downswing of the action potential is replaced in this nonlinear integrating fire model by an explicit reset. The nonlinearity that we find here is that of the exponential integrating fire model. So let me summarize. This week we have reduced the Hodgkin-Huxley model to 2 dimensions, and we arrived at a model where spike initiation and spike formation can be nicely analyzed in the phase plane. Now, in this last lecture, I've made a further reduction to 1 dimension. We arrive at a nonlinear integrated fire model, which has a large linear subthreshold part and the exponential nonlinearity. And in this one-dimensional nonlinear integrated fire model, the downswing of the action potential that is modeled in a 2-dimensional case by the W variable, the downswing of the action potential is replaced by a simple reset of the voltage variable. Now, this kind of model with a broad linear subthreshold regime will be the starting point for the discussions of coding and noise in the next few weeks. Please take a moment for the quiz and don't forget the assignments. Hope to see you again next week for exciting new material.